The next step ought to be pretty obvious to you. So hopefully I pointed this out. Your mind leapt immediately to what it is, which is 1 over the Reynolds number. So we can quickly replace that. So there's the Reynolds number in that position. And so now we will need some scales for time and for pressure. And, it's kind of obvious what we should do for pressure. This is, as I said, looks a lot like the dynamic pressure. It's just 2 times the dynamic pressure. So if we define a dimensionless pressure that's equal to the pressure divided by rho u infinity squared, that'll probably get rid of that term, right? So we'll solve that for P, and P will be rho u infinity squared times the dimensionless pressure, and we'll plug that in for this, and that'll get rid of these terms here. We'll have a dimensionless pressure defined in this way. Same kind of idea for time here. So L over U infinity, that is a length divided by a velocity. That is a time. So that is a characteristic time. So once again, we can just say, all right, let's define a time. Sometimes people just use tau. I'll use tau with a squiggle just to keep it consistent with my others. So my dimensionless one will have a squiggle, but you'll see that sometimes just with a tau instead of a t. But at any rate, tau will be defined as our time divided by our time scale, which is L over U infinity. So our length scale divided by our velocity. So that's equal to just T times U infinity over L. So that should come out to be meters per second divided by meters gives you 1 over seconds times seconds. So that's dimensionless also. So those are our 2 new dimensionless scales. I obviously need to solve this one for t in order to substitute it in for this t here. So I'm going to solve that for t. T is equal to tau tilde times L divided by U infinity. So that's what's going to go into here. So I'm going to plug this into there, that into there, and then we're going to be in truly dimensionless form with all dimensionless variables and no dimensional terms at all. So that's going to look like I had before. I had L over U infinity times du tilde dt, but now I'm substituting in my t equals tau L over U infinity in that denominator. And then I've got a bunch of already dimensionless terms, which is nice. These are all, we took care of these already. Equals minus 1 over rho, and now we've got the pressure term. So we had rho U infinity squared before, and now we're going to have the P substitution. So we have d P tilde, and we said that P was equal to P tilde times rho U infinity squared. So rho U infinity squared up there divided by the dimensionless x, so divided by taking with respect to dimensionless x, and then we have still the 1 over the Reynolds number based on our characteristic length scale times d squared u tilde dx squared plus d squared u tilde dy tilde squared. So those are our, that's looking good. So you can see I can pull this constant out of this derivative. It's going to cancel that. And of course, this is going to pop up here and cancel this stuff. So it's going to be U infinity times L, U over U infinity times L. So that's going to cancel this stuff. So we end up with our final and totally dimensionless form of the x momentum equation, du tilde d tau tilde plus u tilde du tilde dx tilde plus v tilde du tilde dy tilde equals minus dp tilde dx tilde plus 1 over the Reynolds number based on our characteristic length times the Laplacian of u tilde. All right, so that's not bad. And I'm not going to show you, but I believe you will believe that you can do this exact same thing for the y momentum equation. So we have u dv dx plus v dv dy all with tildes, minus dp tilde dy tilde, plus 1 over the Reynolds number based on L of the Laplacian of v tilde. So those are my two momentum equations in completely dimensionless form. And I have du tilde dx tilde plus dv tilde dy tilde is equal to 0 for my conservation of mass equation. This is all with these definitions. So all my dimensionless variables. Tau is equal to t u infinity over L. U tilde is equal to u over u infinity. V tilde is equal to v over some characteristic velocity u infinity. X tilde is x over some characteristic length. Y tilde is y over some characteristic length. And finally, our pressure, which is the regular pressure divided by twice the dynamic pressure, but rho u infinity squared. So that is your complete dimensionless representation of the Navier-Stokes equations. You can use other non-dimensionalizations. Occasionally people do. As I say, one of the most common ones is sometimes people want to have y go from some h scale instead of some L scale, and that changes some things. You end up with some L over h terms up in here, which is fine. But this is the one that has the least extraneous terms, the fewest numbers of terms. Everything is non-dimensionalized with respect to one characteristic velocity, one characteristic length. And now once you have a characteristic velocity and characteristic length, everything else is defined. So that's what you do. And how do you choose those characteristic lengths and velocities? Really depends on the problem. So we'll start looking at that next.